face. You have to do this minus that because one is oriented up, the other one's oriented down. And so this is the total of the vertical flux. But of course, this is just, if you look at it, that's nothing more than and here's a backwards application of the fundamental theorem of calculus. I go from this difference to that. And so I'm omitting a limit here and using like dz rather than an explicit limit, but you could, well, anyway, that by fundamental theorem of calculus should give you partial r partial z dx by dz. And so then look what you got. You got partial p partial x, partial q partial y, partial r partial z. You add these together, and that gets you the net flux through the little cylinder is equal to the integral of the divergence through the cylinder, which is exactly the divergence theorem. So it comes through a somewhat clever integration of Green's theorem in divergence form is one way to think of it. I do have a proof for this for a graph, and it again involves just fundamental theorem of calculus on the parameterization of the graph and junk. Now, so I just did it for one little pillbox, right? Well, I mean, one little cylinder. What about other shapes? Mr. Gibson, what do you think about other shapes? If we can do it for, I don't even think I have the picture in here, do I? No, I do not. All right, this is a hard one. This is hard for me to draw this. Anyway, we'll do more examples after break, after all the other 20 people in this class should see examples. Well, there's not 20 people, the other 10 people were missing. So, okay, so I just kind of sketched for you the proof of Green's theorem for like a little cylinder, right? And I think you can see that if I could do it for a little cylinder, I can just as well do it for a little cube, right? Then what do? You take your simple solid and you break it into cubes. Cubes tessellate. Thank you, Mike. But you see what's going to happen with the cubes. I mean, and despite the poorness of my picture, I think you can already see what's going to happen when you add up the flux through each cube. What happens to the interior faces? The fluxes through the interior faces are equal and opposite in every adjoining cube. The only thing you're left with is the outward flux. And yet, the sum of the integrals over the bulk of these subcubes added all together gives you the net volume integral of the divergence. The argument is almost the same as Green's theorem, as Stokes' theorem, in terms of parsing it into sub-objects which have interior faces which cancel out. You might expect that this could be done in n dimensions. You would be right. I taught that earlier today. Sort of, kind of debatable. I don't know. I almost taught it earlier today. Sort of. I know books where it is written clearly. Let me say that. But anyway, we will do more examples after break. Have a good break, you guys. Thank you for bearing with me.